In an earlier video, we considered counting where we have n items and we want to select r of them. And the items that have already been selected for one position cannot be selected again. Now let's implement that same rule. The only difference now is, suppose that the order in which those are selected is not of importance. So an example of this might be, I have 5 people and I'm going to select 2 of them to help me move furniture. Now we can all agree that depending on which 2 people I select, I might get a different level of help, but it doesn't matter whether I call Sam or Julie first, or then first call Julie and then call Sam, first call Sam, then call Julie. The point is Sam and Julie are both helping me in the same capacity. So that would be a situation where, I can't call Sam twice and have him serve as 2 different people, nor can I do that to Julie. She's only one person, he's only one person. So I can't select the same person twice, but also the order in which I call them is not important because they're going to be completing the same task. Now, each of these types of outcomes where you can't select again from those n people, you're going to select r of them, and the order in which they're selected is not important, we call this a combination. Now, let me pause for a second here and talk about combinations, because when we hear the word combination, we think of a lock. And you could definitely agree that the order in which you put the 3 numbers on your little scrolly lock does make a difference. But in mathematics, a permutation is actually a more valid word to describe the numbers that you put in on your lock dial. A combination in mathematics is actually where the order doesn't matter. So we would call them a lock permutation in mathematics. So before we get into this, we need to think about how many ways are there to rearrange the same r things. Like, I'm going to select r things and imagine a pond here, and maybe I have a fish and I have a starfish, and maybe I have what else can I draw? I can't draw much. I'll just say that's a rock. And I'm going to select 2 items from this pond. Well, you can probably agree the order in which I draw them doesn't matter. And if I remove the fish and then I remove the rock, that fish rock is the same thing as rock fish, because at the end of the day, if I tell somebody what I caught a fish and I caught a rock. Okay, so in this case, there are 2 ways to rearrange the same 2 objects, right? It's put the first one first and the second one second, or put the first one second and put the second one first. So if I think about this as a mathematical statement, if I have 2 items, well, for the first item, I can select any one of the 2 of them, but then for the second one, I can only select the remaining one. And so there are 2 rearrangements of same 2 items. What if I had 3 items? How many ways could I rearrange those? Well, in this analogy, you might think I could catch fish, then starfish, then rock, or fish, then rock, then starfish, starfish, then fish, then rock, starfish, then rock, then fish. Or I could first catch the rock and then a starfish and then a fish, or the rock and then the fish and then the starfish. So there are 6 rearrangements of those same 3 items. Now mathematically, now that we know how to count without repetition, there are 3 possible things that I could catch first: the fish, the starfish, or the rock. But then depending on which one I catch, there are only 2 items remaining in the pond. And then there's only 1 item remaining in the pond. And 3 times 2 times 1 is 6 rearrangements. What about r of the items? Well, the idea is the same, because if I take r items and I ask how many ways I could rearrange them, there's r possibilities for the first one, there's r minus 1 possibilities for the second one, r minus 2, right? We're just subtracting 1 off each time, all the way down to 1. Well, that is really just the definition of R factorial, and there's R factorial rearrangements of the same R items. This is important because whenever we're doing a permutation, we are actually counting every single one of those rearrangements because order was important. Now, we do not want to count all of those rearrangements of the same R items. We only want to count the number of arrangements that contain, that do not have elements in common. We have R factorial multiples too many. Let's see if we can visualize this. As an example, suppose there are 4 candidates for 2 identical board members, member roles. Both have the same role. So it doesn't really matter whether we call Jane or Sam first. The point is Jane and Sam are forming the board, and that's just really one possibility. Now, if I went about this in the same way, where I look at board member 1 and board member 2, and I draw a tree diagram. For board member 1, I could have candidate 1, candidate 2, candidate 3, or candidate 4. Now, if I select candidate 1 first, doing this the way we used to do it, this could be 2, 3, or 4. If board member 1 is candidate 2, then I could have 1, 3, or 4 for candidate 2. Or board member 2. And if it was board member 3 that was selected for the first position, then I could have 1, 2, and 4 for the second board member. And if candidate 4 was selected, then I could have 1, 2, or 3 as the second board member. And here's the thing. We're counting 1, 2. So 1, 2 is one possibility, but notice also that then down here I have 2, 1, and those are exactly the same. That's exactly the same board of people. Now similarly for 1, 3, I also have down here 3, 1, and that's again the same board. And so this looks like there's 4 distinct boards that we have so far, but there's actually only 2. There's one board involving members 1 and 2, and one board involving members 1 and 3. If I keep on going in this fashion, 1, 4 is actually the same as 4, 1. And what I'm going to count is the number of distinct colors here, because the number of colors indicates the number of different boards. So 2, 3 is the same thing as 3, 2. And we're going to run out of colors here. Let's go with this one. 2, 4 is the same thing as 4, 2, to be down here. I have one more. I have 3, 4, and I have 4, 3. I have 3, 4 right there, and I have 4, 3 at the bottom. So how many distinct colors are there? Well, there's 1, 2, 3. Blue, green, red, orange, that's 4. Purple, that's 5. And black, that's 6. So even though there are 4 times 3 total arrangements, there are only 6 distinct boards that I could form. Now, what was that? Well, if I took 4 times 3, that gave me 12. But 12 contains 2 multiples of the same 6. Contains 2 multiples of the same 6 distinct boards. So what I need to do is I need to take that 4 times 3 and divide it by the number of ways that I could arrange those same 2 board members. That's going to give me 4 times 3 divided by 2, which is 6. Now, one thing that we also know is that the 4 times 3 is really the number of permutations of 4 candidates, selecting 2 of them from that group, dividing that result by 2. Now 2 is the number of rearrangements of the same R people. And so I could also say that what this really is the number of permutations of 4 people taken 2 at a time divided by 2 factorial. Now the 2 factorial is the number of people that I'm selecting at a time, and we have already said that if there are R people, okay, so from n select R, that what we need to essentially do here is divide out the number of duplicates, the extra multiples that we have. Well, we have R factorial multiples of the same R people. And so if I want to figure out the number of distinct boards omitting those duplicates, the same rearrangements, different rearrangements of the same 2 people, thus the same board, I have to divide out the number of duplicates. So now let's reformulate our statement with an equation. Suppose you want to count the number of ways R items can be chosen from n of them, and that the following 2 principles apply. Items that have already been selected cannot be selected again. The order in which those items are selected is not important, so we don't want to count those rearrangements. So that's going to be called the number of combinations, and the number of combinations of n things choosing R from them is the number of permutations divided by the number of rearrangements. So we want to divide out those extra multiples. The formula for a permutation is n factorial divided by n minus R quantity factorial, as we've seen before, and then that is just p of n comma r, and we're dividing that whole thing by r factorial, again to divide out those multiple rearrangements. And then if we do a little bit of algebra here, we put this thing over 1 and multiply the division of 2 fractions by the reciprocal of the denominator, we actually get n factorial over r factorial times n minus r factorial. Now, once again, the reason we're doing this is because if we had 1,000 candidates for a board of, say, 30 board members, then there's going to be a lot of multiplication and division that's going to be taking place. And so to avoid that, this nice compact formula will do that work for us. So example 4 revisited, where we had these 4 candidates with 2 identical board member roles. Well, that would be the number of combinations of 4 members. Pick 2 of them, order doesn't matter. Here n is 4, r is 2, so this will be 4 factorial divided by r factorial times 4 minus 2 factorial. Again, you can't distribute factorial across subtraction, so this would be 4 factorial divided by 2 factorial times 4 minus 2 factorial. So this is 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. I could cancel out that pair, and notice I have 4 times 3, which is 12, divided by 2 gives me 6. Now, a lot of times we use a calculator to do this, so just like when we did with permutations, you can figure out how to do this on a graphing calculator. We'll do this in Desmos. So using the same utility, if we open this keyboard up, go to Functions, we go all the way down until we get to Number Theory. Now look, there's an NCR button, and if you press that, 4, 2, lo and behold, we get 6, which is the same answer as if we did it by plugging things into the formula. Let's take a look at one more example. Suppose a computer manufacturer will feature 3 of its 10 new PCs in an advertisement. How many possible ads can it create? Well, we can probably agree that we're not going to feature the same PC twice, because that wouldn't be very helpful. We want to pick 3 different PCs to advertise. Maybe we don't want to pick more than that because it's just too much information, so we're going to pick 3 of the 10 PCs to advertise. So here we're going to select 3 from the possible 10, which is n, excuse me. And the order in which we feature those is not going to be important. I mean, we're going to assume that here, that we're just going to advertise for all 3 of them. So the order in which we pick them shouldn't matter. And so what do we have to do now? Well, we have to figure out the number of distinct combinations of 10 items taken 3 at a time. So I could kind of draw out a tree diagram again. So the first PC that gets featured could be any one of the 10. And like I had said previously, the goal here is not to list them all out, but we just want to get a visualization of what we're doing. And we could advertise PC 2 through 10. But keep in mind that 1, 2, 10, and 10 down here, we'd also have 2 and 1. We don't want to count those as distinct possibilities because in the end, both 1 and 2 are getting advertised. So the number of combinations of 10 items, selecting 3 from there, and I won't do the third PC column, but we can now calculate it in here. And by the way, you can also just type in NCR, 10, 3. There's 120 possible ads that we can create. Now, if it did say, hey, you know, the order in which you feature them, we're going to put the first PC at the top and then the second PC and the third PC, then perhaps we can make an argument that the order would matter. Here, since we're working with combinations, I'm implying that we're just going to pick 3 of them. But if the order did matter, then it would be the number of permutations of 10 items taken 3 at a time.